Okay, whenever you're ready, go ahead, Group A. I'll get some water. Huh? Very good. Be very nice householder transformation.
Okay, so we can start now.
Mm-hmm.
So in this task, we use a fashion means data set. So turn this image into a data matrix. But there are some features is that close image have a lot of black background pixels, so we can show something of the output. Okay, next page. Uh, this graph shows a numerical characteristic of our matrix as we subsample them from 100% down to 10%. And this is where we found something very interesting. So start at the top left chart. Here we see the matrix norms as expect when we reduce the dimension by throwing away pixels. The overall energy or magnitude of the matrix goes down. So you can see that 10% and 75% and then 100%. So it grows negative slope. And the top right and the bottom left charts, we look at the smallest singular value at a 100% full resolution. It is exactly 0. Because the fashion means images contain a massive amount of identical black background pixels. Yeah, so these redundant features make our original matrix rank deficient.
Yeah.
So it shows 0 here. And because the smallest singular value is 0, our condition number at 100% becomes infinite. So this is why the data point is missing on the bottom left chart.
Shows up to infinity. Yeah, nice.
Yeah, and however, look at what happened when we subsample down to 25% and 10%. The condition number drops to around 40,000, and throwing away 90% of our data actually improve the matrix condition. So by dropping the pixels, we accidentally filtered out the useless background noise, I think. So allowing the matrix to become full rank again. And that's the bottom right chart, the distribution curve for all 3 levels perfectly overlap like that. And this proves that our random sampling was unbiased. Even at like 10%, we maintain the exact same feature distribution as the original image.
But let me ask you this: why does your histogram go below 0? The value of the pixel is between 0 and 1, right? So there should be 255. Then you normalize between 0 and 1, right? So why do you go below?
Yeah,
0?
you say that. Maybe I think it's just like a graph and.
So did you? So is this the? So you did the Gaussian interpolation here? Of the? It's not a histogram. Is it the Gaussian interpolation? Did you do kernel? Did you plot the kernel of the? Yeah. Do you remember?
I'm not sure.
Okay, yeah, because the 0 pixel should correspond to
Yeah, it should go like stop at 0.
Exactly.
I think it's maybe like the code of drawing this picture.
Just checking because you could have also
Okay.
normalized that to be zero mean, let's say zero mean and unitary variance, but even in the case, yeah, in the case the mean should be below zero, right? So it's probably just the kernel. When you plot the histogram, you did an interpolation with the Gaussian curve, and so that's why it went below zero and above one. Okay, go ahead.
Okay, so next page. So we go on task 1. We moving on compare the performance of classical and modified Grimsby. And starting with the top left one, we look at the execution time while both methods become extremely fast at lower dimensions. Then we can clearly see that at 100% for resolution, the modified one, which orange one is noticed that it is slower than the blue one, the classic one.
Yeah, because you have an extra normalization, right? So that brings the complexity higher, but improves the numerical stability. So go ahead.
It's because that it requires the modified one requires continuous update the remain vector in its inner loop, so that it takes more time. And but the speed maybe is not everything. It's like we can look at the top right one. It's showing the orthogonality arrow on a log scale. And at 100% dimension, both methods fail completely due to the ring deficiency we discussed earlier. So that the arrow hits to like 1. But we can look at the 25% and 10% dimension. The orange one has a consistently lower than the blue one. So we can see that the modified one is better than the classic one.
Yeah, it's more.
So this can prove that the modifier successfully reduce round-off errors and provides much stability. And the bottom left chart, it shows the relative error of our solution exposed. Both methods struggle heavily at 100%. And because the metric the metric is a condition, so maybe that it is always like high error on for the 100% one, but the error also drops dramatically at lower dimension. The log scale, so log scale, so it has a dramatic drop like that. And
so the
finally,
the test accuracy here is classification, right?
Yeah, the blue one is classification.
Very nice. So you have the error and then you have the classification. Okay, very good.
Yeah,
nice.
And the last one, the bottom right chart gives us a ultimate test accuracy. So the accuracy is identical for both methods. More importantly, it dropped from like 784 dimensions down to just 78. Actually increased our accuracy from about 98.5 to over 99. So in summary, the modified Grimsby trades a little bit of computational speed for better numerical stable, and aggressive subsampling remains the best strategy to boost both efficiency and accuracy. Okay, next page. So next page, we have now add the householder reflection on it's a green bar to our dashboard. So we look at the top left chart again, the execution time we can saw that the householder took about 15 seconds, make it significantly slower than Greensmith. This happened because building a full Q matrix step by step in our Python loop requires heavy matrix multiplication.
Correct.
So, but we get in return for that time, we can see the top right chart, the orthogonally arrow. This is the most important finding at the 100% dimension where our metric is highly rank deficient. The blue and orange one we saw earlier is completely break down with an error of 1, but look at the green one, it stays firmly at the bottom, near 10 to the power of negative 14.
Very nice, right? Very nice. Very nice.
So the householder gives us absolute numerical stable and is completely immune to rank deficiency.
Very nice, right?
And then in the bottom left chart, we look at the relative error of our solution. X at 100% householder finds a different specific solution than the NumPy baseline, and causing a spike on the relative error. However, once we drop down to the full rank 10% dimension, all three methods converge perfectly to the true solution. So, and finally, the bottom right chart confirms our previous observation. Despite the massive difference in stability and time, the test accuracy is exactly the same across all three methods. Yeah, and once again, the aggressive subsample 10% dimension give us a highest accuracy. So the next page, on text tree, we go on given rotation, represented by the red bars. So we can look at the top left chart. Givens took nearly like 30 seconds to run because it operates zeroing out elements one by one using 2D rotations. So since our image metric is dense and packed with numbers, this element by element approach is extremely inefficient. But however, at the top right one, for the orthogonally arrow, just like householder, the red one stay perfectly at the bottom near the 0. So completely ignoring the rank deficiency that destroy Greensmith. And the bottom left one, we see that the Givens and householder both find different specific solution than the baseline at 100% dimension, causing a spike there. But once the metrics become full rank at 10%, all method converge. And finally, the bottom right chart gives us the biggest takeaway that despite a 30-second difference in speed and massive difference in numerical stability, every method achieved nearly the same test accuracy. And yes, again, the drop in 90% of a pixel gives us a better result. Okay, so next.
Okay, so I will take over with task 4, which was the hierarchical decomposition. And for this one, we selected the householder to be the base because it is the most numerically stable. And the results were good. The accuracy was not affected. It was like pretty much the same as with the normal decomposition, and there were not big differences based on the block size either. It was all like 10 to the power of minus 12 or minus 13. I will have a plot for this later. And then the other big question, this was the time that it takes for the computation, right? How that affects that. And obviously the trade-off here is that as you increase the B, the amount of blocks, you can get more parallelization, and the sort of like first level decomposition becomes simpler, but then the part where you have to combine it into the final metric becomes more demanding. And what we found in the experiment is that using B4 was like the perfect balance. If you look at the plot on the next slide, it is very clear from that. So can you show yes.
Very nice, very nice.
Here you can see that, yeah, if the block size is too small, you don't get any of the benefits. And when it becomes too large, then you have too much overhead and it slows down. So you can see that even the variance, there's a big difference, right? This is over multiple runs.
Very nice. So the 4 is also the smallest variance. Very nice. Very nice.
Yes, exactly. So this was almost surprisingly a clear winner, but it makes sense that it's somewhere around the middle. So it's a good balance between the two forces that affect this. Okay, and
see here what
then
I always tell you, right? That if you have the enemy of every algorithm are hyperparameters, right? Because the more if you have a hyperparameter, then you have to tune it, and tuning the hyperparameter consumes a lot of time. Go ahead.
Right, but the important thing is the runtime. You can see there's a very big difference, right? Like if you look at the relative difference, it's multiples. But for the accuracy, the results were not very different. On the next slide, is there okay, well, there was supposed to be a slide showing the accuracies, but okay, I can just comment on it. Pretty much like the accuracy does not change based on the B. It's always, like I said, like the orthogonality and the reconstruction error are both like 10 to the power of oh yeah, there we go.
There we go. Let me see this plot.
So yeah, there are big differences. Obviously, like you see, the only big effect here is the subsampling level, which, the 100% can only be done for B2 because of the shape of the matrix. That's the
Why
reason.
didn't you order the subsampling level? Why is you have the 10, 125? You confuse me so much. Could you imagine? God damn it.
Yeah, that's a good question. Yeah.
Because in the previous one, it was 125 and 10. And here you scrambled everything, so that no 2 points, no 2 points makes sense. Okay.
It's just a test of attention, to
gee, you don't need to test my attention, guys. Don't be cruel. Yeah. Very good, very good.
Okay, and then the next slide, there's some discussion about what this means for the usefulness, I guess, of this approach, which is obviously that the parallelism is very useful in certain cases, like when you have multiple machines. Unless you find a way to parallelize it, you cannot use multiple machines, or even, I guess, multiple cores. And also, if you have matrices that are too big to fit into memory, then you also want to find a way to break it down into a simpler task that you can perform efficiently. So that's pretty much the answer to how this affects the large scale and distributed systems, that for them it is generally very useful because it allows them to make use of, say, a bigger amount of smaller computational units.
Yeah, it's good. It's good. Let me see this. Okay, who's going to tell me about this?
And I will take this part and text is rotation and formation.
Well, guys, I wish they give me enough money to buy microphones for all of you guys. Some of you guys have some shit, some very bad microphones. It seems like you're calling me from underwater. Go ahead. If I ask you to repeat, it's because of your microphone. Okay, I'm not deaf. Just bear with me. Go ahead. Go ahead.
And I'm sorry for that because my laptop broke like a month ago, so this is
I understand.
the temporary one.
Very good. Very good. Very good. Go ahead. Go ahead.
Okay, and from that one, with construction errors, and they are all very low. So I think the numerical verification of A is almost equals to RP, and the second chart is the orthography error of R, and it's same as the text one.
Just a second. Just a second. Just a second. Can you tell me? Let's start a little bit back, because the fifth one is the fifth. I mean, the last challenge is always the last task is always the one that makes the most sense, the one that requires the most discussion. Did this make sense to you? I mean, do you understand why I suggested this decomposition? Does it make sense to you?
Sorry?
Say, does this decomposition make sense? Right, because the decomposition that we discussed before, right? They made sense from a numerical perspective, say, right? Because it was some sort of simpler numerical structure, right? So we spend a lot of time saying, well, the type of matrices that we like are triangular matrices, because when we solve a system of equation, we use forward and backward substitution. We like unitary matrices because the inverse becomes just the transpose. So it makes sense that we want to decompose things into this type of structures. And so that's why we had all these different decomposition like QR, LU, and so on and so forth. So, but this decomposition was more like maybe, let's say, physics related, right? Because you could say, well, if you have a certain scene, then the view of a camera can be seen as this decomposition. And yeah. Does it make sense to you? Tell me a little bit about tell me a little bit how you see the decomposition, right, in your mind, if it makes sense.
I think it makes sense. Since it's quite similar to the text one we did.
To the what?
To the result in the test one.
Okay. Okay. Okay.
Yeah.
Go ahead. Go ahead.
And the orthography error of R is almost 1 at the 100%, and very low in 20% and 10% of the level, same as text one.
Yeah, because the size of the matrix goes down, right? So you should,
and
to do this error, you should normalize by the number of elements, right? So that you can see that if you normalize by the number of elements. Anyway, go ahead.
And the conditional number of A is very big in the 100%.
Because it's a condition.
Yeah. And almost the same at 20, 25%, 10%, which is 7.1 and 4.3 here. And this is the spectrum of M. The full resolution matrix is a much longer tail of very small eigenvalues, like here. It's almost equals to 0 here.
Yeah.
And 20% and 10% matrix have more compact spectrum, which is consistent with their smaller condition numbers and better stability.
Yeah. That's what we always say, right? That even if a matrix is full rank, if it has a lot of eigenvalues close to 0, then it's very numerically unstable, right? So mathematically, you have a distinction between an eigenvalue being equal to 0 and an eigenvalue being greater than 0. But numerically, being close to 0, has the same effect of introducing a lot of instability, right? Go ahead.
And the spectrum also explains why the computation of P and the corresponding vector R is more sensitive in the 100% case.
Very good. Very good.
And the last one is the shaped diagonal of P that gives a rough pixel-wise visualization of deformation factor in the polar decomposition. The brighter regions here correspond to large diagonal entries
Yeah.
and indicate stronger scaling along those coordinate directions. But this visualization is only partial because the fourth dimension is encoded by the entire matrix P, not only its diagonal.
I see.
And I think that's all.
This is P.
Yeah.
Then you do the reshape of 28 by 28. So that's the original. That's the original version of the image.
Yeah.
Yeah, there's not much to read here, right? Because, for example, it would have been nice to see if it made sense, right? For example, the background, right? The background doesn't stretch, but that's not what you're saying here. There's no clear pattern. Interesting. Okay, go ahead.
That's all.
Okay, good. Okay. Very nice. Okay. Yeah, no comment. Yeah, so remember from next challenge, you guys can decide how to form the groups, right? So hopefully we still have 2 groups in the next challenge, otherwise we'll just have 1 group and that's it. Okay, go ahead, group A. You guys, no, this was group A. So is group B ready? You guys are all here?
Yes.
Okay, go ahead.
And I think in our group we only have like 2 people.
No worries. From next challenge, we just have 1 group and we give
Maybe think. Okay. Yes.
Your microphone is a little bit terrible. I hope you can solve this issue. Hello.
I think 2 of our teammates like dropped the course, so I do the text 3 and text 4 just like in 30 minutes, so I don't think I have prepared well. So
Don't worry, don't worry. We just discuss it all together. Okay, this one here we saw it already. Yeah.
Okay. Yes, so here is basically the same with the group A, and we can see as the dimension reduce, the norm reduce, which is like when the condition number increase as the dimension reduce.
Mhm, mhm.
Here is the numerical range and the dimension, and when the dimension is 70, 184, the range is the same, but when it comes to 196 and 78, the actual range is below the theoretical max range, which tells us that in this two rank the matrix is rank deficient, and this one can call back to the last picture with about the conditional number. Like when it comes to a conditional number, it was a picture like this, and the small singular value is it's
It goes to 0. Yeah.
and here is
Good.
distribution, and
So you said you mostly,
we
yeah, you
can-
mostly lose the background. Yeah. Go ahead. Go ahead.
Yes. So when it comes to like random sampling, it may take lots of like the black pixels. So there's no any changes. So it goes to like this. Okay, so here is the test one, and we have like picture another page. Okay, so when it comes to the execution time, the MGS is basically a little bit basically larger than the CGS, and when it comes to the orthogonality error, the CGS is larger than the MGS because like the MGS will continues to update its picture, and the CGS just like use to calculate the truth at the last time. So it will be larger than the MGS. And when it comes to the relative error, we can see that MGS is a little bit larger than the CGS, which I think is a little bit different from the last group. And it is because like when it comes to the barcode it is used the SVD to get the minimum norm solution, and when it comes to when it use back substitution, if the diagonal is 0, it will let the x becomes 0 and it continues to solve the problem.
Yeah.
When we if we calculate like we minus each other, the modified NGS become larger than the CGS.
I see.
Okay. And for the training residual, the NGS is larger than when we see the A1, the NGS is larger than the CGS. Okay, and here we comes to the part task 2. Okay, so
Yeah, the execution time goes down. Yeah. So you code this. You code this, right? Yeah.
Yes. And this like is the just like this is the only difference point I think that is different from the last group, like why the execution time is like lowering than the like smaller than the MGS and CGS, which the last group is like the householder is larger than MGS. And so I looked back to my code and found out that when we are using the branch mix, we use the for loop to calculate the dot product, and when it runs one time, the Python has to like calculate one time, and so when it is at the A1, it will calculate like millions of times, tens of
So you learned the
hundreds
lesson.
of.
Yeah. So you learned the lesson that yeah. The algorithm can always be slower if you code it if you code it poorly. Yeah, it doesn't matter the theoretical complexity. You can always make the complexity higher by doing wrong coding. Yeah, go ahead.
And we use the householder to. We didn't use any inner loop in the householder. We just like give all the total matrix, I think, into the numpy and just assign it to the new R. Yes.
Nice.
So I think that's the reason why our execution time is smaller than the. Okay. And so I think I'll continue. And the rest of it is mainly the same with the group A. And so when it comes to the exogenity error, the A1 matrix, the NGS has an error of about 29, and the householder pushed the error down to almost equals to 0. Remember this here is the log scale. And so, and that the reason is because the householder didn't project the vector one by one. It just used the mirror reflections to zero out the blocks of the element below the die. Okay. Okay, so next we're going to talk about the relative error. So the relative error for A1 and A3 stick to like 10 to 12 and 10 of 5. And this happens because the matrices are rank deficient, meaning that D squares is highly non-unique, and our back substitution locks the extra free variables to 0, so it points to a different location in the vector space compared to the minimum norm solution. So, so next is the okay. Here's the text 1 to 4, and the 2. I think the 2 dropout teammates should do this part, and I found out this morning they didn't make it, so I just made it. Like I didn't do it very
thoroughly.
I didn't have much time to prepare it. It's so here is the for type 2 task 1 and task 4. And I think we just need more time to just like figure out why task 3 and 4 look like this.
Yeah, you need to fix your Graham Schmidt, because it's really shooting off over all the overall the statistics, right? Also the error is very large. The orthogonality error, the stability is very low. Yeah, probably if you do it, if you also do it element-wise, it's also very unstable numerically. That's why you have such a large orthogonality error.
The CGS and NGS part, or the
Yeah. That one. You see also in the orthogonality, right? In this Q transpose Q minus I, they have a large error, right? Something there. You see that, you see that they are out of scale. I wonder, because you accumulate, maybe the error accumulates somewhere. Because you said that you do the inner product with the for loop, right? So I wonder. Okay, very good. So I think moving forward, we'll just have one group, and we'll just continue this way. The class is very chill. Unfortunately, this year the class is small. So go ahead. Anything else that you want to present us?
yes, it's fine.
Okay, good.
So test 5, we are focused on rotation and deformation via polar decomposition. And I just watched the previous group slides and found there's a lot of difference from our result.
Yeah.
I'm here to check if I'm doing anything wrong. Okay. Look at the numeric properties of M. And across all our test case, M constantly exhibited strict numerical symmetry. The matrix is also positive semi-definite. We observe only minor floating point noise, typically around 10 to the minus 7, 10 powers minus 7, which is expected for this operation. I skip pages.
No worry, no rush. No, don't beat yourself up. We'll find the slides. Don't worry.
Okay. Yes. This is what I should told. Okay. Next page. Moving to matrix P, which is the square root of M. P inherits the high numerical symmetry from M with an error margin of approximately 10 powers minus 8. Furthermore, P consistently demonstrates positive eigenvalue characteristics with minimum positive eigenvalues present in all cases. Okay, next page. For the calculation of R, we specifically adopt the pseudo-inverse form of P. We found that the decomposition successfully reconstructed the original matrix A. The relative errors observed were excellent. Okay, next page. A critical verification step is checking the orthogonality of R. We observe that R cannot maintain a perfect identity matrix, especially under rank division or ill condition scenarios. When matrix A approaches singularity, R behaves as what we term a partial isometric rather than a perfect or orthogonal matrix. Next page. To illustrate this, in a A1 test case, the matrix presented a completely singular state. This is proven by the condition number of A being infinite. The severe rank deficiency under certain conditions confirms our expectation for the behavior of R. Next page. Finally, let's consider the impact of subsampling levels on conditioning and orthogonality in the finite condition region. Moving from A2 to A3, stronger subsampling led to a more ill-conditioned system. Specifically, the condition ratio increased by a factor of approximately 1.64, while the overall error did not change monotonically from A1 to A3.
Yep.
The orthogonality error degraded significantly from A2 to A3 with a ratio of 1.38. This leads to the conclusion that overly aggressive subsampling dramatically increases the computational difficulty of preserving numerical orthogonality. Okay, that's it.
Yeah, because the previous group didn't have this issue. They didn't. Also for the A25, they were not. They were yeah. They were doing. It was more monotonic there. Yeah. I wonder what's the difference. Yeah, I mean you choose some different subsampling, so you probably occur different. You observe different numerical results. Okay, very good, guys. 3 minutes. 3 minutes break. Then we talk a little bit about SVD, and then PCA, and then I'll let you guys go. Okay. So I think the class has become a very intimate affair now. It's just the few of us, so you don't have to worry too much about about the grade. So okay, 3 minutes break. You walk around, and then I'll see you back here. Okay, guys. Hello, guys. Hello, guys. So we switched the set of slides that we're looking at because there is no SVD in the other class. So we move to this University of Illinois set of slides, and we do SVD. So the slides are they look much worse. I mean, the graphic of the slides is not very good. It looks like some sort of, I don't know, 1980s, 1990s presentation set from PowerPoint 97, but we shall not complain too much about it. Okay, so as VD, we slowly built toward there, right? So the composition that we saw so far, they all sort of hinted at this other form of this decomposition form. And you will recognize that there is a little bit of ingredients from various decomposition that we already saw before. But basically, in SVD, we decompose the matrix as written here. So we have an n times n matrix. So the decomposition needs not to be a square decomposition. And we have that A is equal to U sigma matrix and then V transpose, okay? So remember the dimension, this is m times n. So what we have is that, why I'm not in presentation mode, sorry guys. Present, I'm trying to keep the tab, okay, this should be good, this should be good. Okay, good. So we have that, we have this m times n matrix, right? So the U is an orthogonal matrix, and it's m times n. V transpose is an orthogonal matrix, also n times n. And then there is a diagonal matrix, which is this delta, which has the size that of the minimum between m and n. Okay? So, yeah, so you see here that we can represent this as the rows of the orthogonal, the orthogonality of the rows is in this direction, and here the orthogonality of the rows is in that direction. Okay. So what happens if we have a non-square matrix? Okay. So the easy case is the case in which we have m equal to n. So these are all square matrices, so nothing happens. So what happens if we have a matrix which is non-square? Then the middle matrix, the sigma matrix, starts having this block diagonal form. So here we're going to have a matrix which is n times n. It's the matrix m times m, and we're going to here have a matrix, a block of m vector, and the number of the rows is n. Here we have a diagonal matrix followed by a O0 matrix, and here we have the matrix there. Okay, so here m is greater than n, right? So this is a wide matrix. So this becomes a tall matrix, and this remains a square matrix. Okay, so m times n is here. Here we have n rows of size m. Here we have a diagonal matrix followed by m minus n times n all zeros. And here we have the square matrix. Okay. So remember that sort of we retain the orthogonality, but only across the submatrices. Okay. So then we have these blocks where we have some other properties where are not satisfied. So what happens is n is greater than m. So if n is greater than m, then this matrix here becomes a tall matrix. So the U matrix remain m times n. The two letters are too close together. The left matrix retains an m times m size. Now the matrix sigma, right? It's a wide matrix, and the diagonal or the subdiagonal of the first n times n contains it's a diagonal matrix. It's a diagonal subblock, and then it's followed by an O0 matrix. And here we have a matrix, right, where the first m rows form an orthogonal. They have an orthogonal property. Okay, so remember, it's a little bit complicated. It's a little bit takes a while to get used to it, right? So, but it's very, very convenient. So remember, the easy case is the case that you usually see when you are solving, let's say, nice problems where everything is square, right? So this is the easy case. M is equal to n. Everything is square. Okay, good. Now remember that This is m times n, right? So here, if m is greater than n, right, then this becomes tall and this becomes wide. Okay, so the u becomes wide and the sigma becomes tall, and here we have a subdiagonal block there. Whether if n is greater than m, then the subdiagonal blocks is here. This is a wide matrix and this is a tall matrix. This is to say that we have a form for all of the possible combinations of m and n. You just have to remember which one we are dealing with, and the decomposition, let's say, will naturally extend to this case. Okay. So in general, right, you want to have a form of the following. So you have A is equal to UR sigma R VR of T, when R, this R indicates that the middle matrix is always kept to be a min m comma n size. Okay, so now if we allow this matrix to be a square k by k, then we can let this be a diagonal matrix, so that then so that then you capture everything nicely, right? You capture everything nicely so that this will always remain square. This becomes m times k, and this always becomes k times n. So the transpose is n times k. Okay, so depending on the context where you are, right, you might use one formulation or the other formulation. Usually having a square matrix in the middle is the best thing to do, because this matrix you can always guarantee which is square, and the dimension which is k is equal to min m comma n. But of course, in different contexts, people could have the need of having the zero padding of the matrix. Doesn't matter. Okay, so let's look at the sigma times sigma formulation, right? So if m is greater than n and we are in this zero padded form, then we take the sigma times sigma is equal to this n times m matrix, right? And here, if we take the sigma times sigma where n is greater than m, then we have this n times n matrix, and this is all zero padded. Okay. So the different, different forms, they preserve different properties. It's not too elegant, okay, but you just have to remember this stuff. So the symbol, let's assume that the matrix A has a singular variable decomposition as U sigma V transfer. Then we look at the eigenpairs formed by A transpose A. Okay, so then if we do this, then you see that the transposition flips the order of the matrix around, everything squares off nicely, right? And the two matrices here, they are orthogonal, so the U transpose U will give you the identity matrix, and so you get the A transpose A is equal to V sigma square V transpose. Okay, so remember that the columns of V are all linearly independent because it's an orthogonal matrix. Then there is a diagonalization form. So we can write B equal to X dx to the minus 1. So we get that the columns of V are the eigenvectors of the matrix A transpose A, and the diagonal entry sigma square are the eigenvalues of A transpose A. Okay, so let's lambda be the eigenvalues of A transpose A, then sigma square is equal to lambda I. Okay, so the eigenvalues of this object, right, are the square of the eigenvalues, are the square of the sigma values. Then, of course, we look at the other direction, in which we do A times A transpose. So in this case, the flipping will be in this order. So what get cancelled is the V transpose in the middle, so that this is equal to U sigma transpose U transpose. And so we have the A times A transpose is equal to U sigma square U transpose. Same thing as before, right? So you get the columns of U are the eigenvectors of the matrix A times A transpose, right? And so then the same, the relationship with the eigenvalues holds. Okay, good. So we understand why we want to have two unitary matrices involved here, so that however you perform the multiplication of the matrix with this transpose, whatever order you take, you have, let's say, the same formulation as orthogonal matrix, diagonal matrix times orthogonal matrix. And then we want to evaluate the SVD of the matrix A. Let's see how we can compute it. So the idea is that the first step is to evaluate the n eigenvectors vi and the eigenvalues lambda I of A transpose A. Then we build the matrix V from the normalized vectors Vi, and the columns are called the right singular vectors. Okay, so right singular vectors. Then we make diagonal entries from the square roots of the eigenvalues. Right, so we know that this one here are the square of the eigenvalues of the matrix delta. So here we put the square root. Notice that the lambda I there, we didn't discuss that this is a positive semi-definite, right? So these values could be imaginary. And then we find the matrix U as by solving this, right? So U is equal to sigma times V transpose. So U times sigma is equal to A times V. And so this is how you train the matrix U. And these are called the left singular vectors of the matrix A. Okay, so the V contains the right singular vectors, and the U contains the left singular vectors of the matrix A. If A is this is a Q&A, right? So yeah, we go through these questions and then we will answer them. So every matrix A is let's say that the matrix A is a singular by decomposition as a U sigma V transpose. Then the matrices U and V are not singular, as is true or false. The matrix sigma can have 0 diagonal entries, so some of the eigenvalues allowed to be 0. The norm of U is equal to 1. The SVD exists when the matrix A is singular, and the algorithm to evaluate the SVD will fail when taking the square root of negative eigenvalues. Let's see what is the answers of this. So singular values are always non-negative. Okay, so the singular values cannot be negative since A transpose A is a positive semi-definite matrix. So remember that we defined this last time. And remember that we had this discussion of whether the A transpose A we had this discussion on whether positive semi-definite matrices are symmetric or not. In this case, A transpose A is symmetric. So here we have that A transpose A is a symmetric positive semi-definite matrix. But as we said, sometimes people say positive semi-definite to indicate symmetric positive semi-definite. So just remember the trick. So the matrix A transpose A is positive semi-definite, right? Because of how it's constructed, right? So because remember that the definition of positive semi-definite is that X transpose B times X is greater than 0 for all X that are not equal to 0. So the matrix is positive semi-definite if we allow for the equality sign. So what do we know about the matrix A transpose A? We apply the definition of positive semi-definite. So we have that this is equal to X transpose AX. So this is AX or everything transpose, and this is equal to the norm of AX, right? And we know that the norm is always positive or equal to 0. So for sure, the matrix A transpose A is positive semi-definite. Okay? It could be equal to 0, and it could be greater than 0. So since the matrix is positive semi-definite, then we know that all the eigenvalues are non-zero. Okay, so we know that B times X equal to lambda X, which is the eigenvalue equation, as you remember from your high school days. This is equal to X transpose B times X equal to X transpose lambda times X, and this is equal to lambda norm of X, and this is always greater than 0, which implies that lambda is always greater than 0. Very good. Okay, so yeah, so everything is okay. So the cost of SVD is proportional to mn squared plus n cube. This comes from how the algorithm is implemented, and there is a proportionality constant which is expressed here, right? So you see here is computing the LU decomposition, math multiplication, and SVD, and you see that the cost of SVD grows logarithmically, right? With a slope equal to 3 right? So you see here that the slope is there. So you see that the O, it's a big O on a cube. Okay, so SVD is a factorization of the matrix M times N as a U sigma V transpose. The matrix U is M times N, the matrix VT is N times N, and sigma is an M times N matrix. Remember that sometimes we have a reduced form in which we fix the sigma in the middle to be a diagonal matrix of size K equal to mean M times N. This is just a reformulation of the decomposition. We are just padding different stuff with 0, and you just have to remember how you pad stuff with 0. So now it becomes U becomes M times K, sigma is a K times K, and V is a N times K. So the columns V are the eigenvectors of the matrix A transpose A. The columns of U are the eigenvectors of the matrix A times A transpose. The first is the right singular vector. The second is the left singular vector. The diagonal entries of the matrix A transpose A are the sigma square root of lambda i's are called the singular values. The singular values are always non-negative since A transpose A is positive semi-definite by definition. Okay, so let's see some application of the singular value decomposition. So if you want to determine a rank of a matrix, right, then you will apply SVD. And at the end of the SVD, you will have that. You will have this. So try to remember this expression because it's very powerful, right? So sometimes you forget how you can rewrite matrix multiplication as a function of the eigenvectors, eigenvalues. Okay. So let's say that we have the SVD of the matrix A, singular value decomposition. Then here we have that we can write the matrix as a linear combination of the eigenvalues and the multiplication of the left eigenvectors and the right eigenvectors transpose. Okay, so you see that this is a column vector and this is a row vector, right? So this is an outer product. So this object, okay, it's an M times N matrix. Okay. So this is not an inner product, this is an outer product, okay? So here you're representing the matrix as the sum of scaled outer product, right? So here we took the M greater than N just for convenience, right? So that we know, but this is always the case, right? So you have the outer product of these objects, right? Since M is greater than N, we are just picking the first N vector U's. The rest are multiplied, are zeroed out by this block of all zeros. And so you're saying that the matrix A can be represented as the linear combination of these outer products, okay? So if you want to multiply two matrices, right? Or let's say you want to multiply a matrix by a vector, you can use this formulation. You can use this formulation to rewrite the matrix multiplication as a sum, let's say, of inner products and outer products, okay? So I think most of you understand that when you multiply the matrix A and B, you can write this as the sum of inner products element-wise, but you can also say, you also represent it as the sum of outer products when you use this this representation, okay? Okay, very good. So what is the rank of A? The rank of A will be equal to the number of non-zero eigenvalues, right? So you will see in this decomposition how many of the sigmas are greater than 0, and that will make you happy. Okay? So the rank of a matrix is always can always be represented like this. Okay, so for a general rectangular matrix A with dimension M times M, the reduces VD. Remember there is this formulation M times K, K times K, K times N. So if you have some eigenvalues that are equal to 0, then you can further reduce this object to be the rank. Okay, so you can reduce this to have a rank of R. So you look at this diagonal structure and you see how many are different from 0. And then you will declare that to be your rank. So you can further reduce the K to be the rank. And remember, I want to say something. I want to say something. Yeah, what did I want to say? Yeah, so this K can become the rank of your matrix. Okay. So usually when you do some numerical operations, usually the way in which the sigma is presented to you are from the largest to the smallest eigenvector. So usually you will want to reorder the elements of this matrix. Of course, reordering these objects means that you pre and post multiply by a permutation matrix, right? So it's not you're not changing the final results, right? So if you permute these elements, you need to permute this element and permute this element. This is, of course, all permutation invariant, because you can look at here this representation, right? So in the representation is total product, it's clear that we can re-index the elements as we want because the summation is commutative, right? So no big difference there. And so usually people will go from the largest to the smallest. Okay, so that if you have any 0 eigenvalues, they will be the last eigenvalues in your in the output of your SVD algorithm. Very good. So the rank of a matrix, the rank of A equals the number of non-zero singular value, which is the same as the number of non-zero diagonal entries of sigma. Rounding errors might lead to small but non-zero singular values in a rank-deficient matrix. Hence, the rank of a matrix determined by the number of non-zero singular value is sometimes called the effective rank. Okay. So if somebody talks about an effective rank, means that they chose a certain threshold for numerical stability, and they said, well, any eigenvalues which is less than 10 to the minus 3 is going to create numerical problems. So I'm going to call that the effective rank. The right singular values, so the columns of V, correspond to vanishing singular values in the span of the null space of A. And the left singular values, the columns of U, corresponding to non-zero singular values, correspond to the span of the range of A. Okay, so one is the null space and the other one is the range. Pseudo inverse. Okay, so the problem is that if A is rank deficient, then sigma is not invertible. So how do you fix this? We go to the pseudo inverse. So for the pseudo inverse, we will take this matrix here, where we take the inverse of the eigenvector of the singular values. If the singular values is different than 0, but if the singular value is equal to 0, then we set this to be exactly equal to 0. Very nice. Then the pseudo inverse of the matrix A will be this A plus, which will be equal to V sigma plus U transpose. So let's see. So you see that we recovered the concept of matrix inverse that we had before. So let's discuss a little bit about matrix norms, because so far you guys only saw the Frobenius norm, which is not very interesting. So the Euclidean norms of an orthogonal matrix is equal to 1. Okay, so let's say that we have an orthogonal matrix U, and we want to look at the Euclidean norm as follows. We want to look at the vector with norm 1, and we are looking for the vector of norm 1 that maximizes U multiplied by the norm of U multiplied by X. Okay, so what we have is that we have a norm for vectors. And now we want to use the norm for vectors to induce a norm over the matrix U. So what we do here is that we allow the vector X to have any direction, but we fix the norm. So we say, among what we say this, that we will call the Euclidean norm of the matrix U as the largest norm of the vector that I obtain when hitting the matrix U with a vector X of unitary norm. Very good. So when I have this U times X, I know I can write it in this way, right? So square root of U X transpose U times X. And since U is unitary, we know that this will not change the norm of the vector X. So this becomes X transpose X. So the induced norm by the Euclidean norm on the unitary matrix U, but an orthonormal matrix U is equal to 1. Very good. Then I will convince you that the Euclidean norm of a matrix is given by the largest singular value. Okay, good. So we have the induced norm on the matrix A, which is the maximum across all the possible vectors of norm 1 of A times X. Okay. Then what we do is that we take the singular value decomposition here. So we have a U sigma V transpose times X, and we take the max over 1. But we just said that the U is unitary, right? So this will not change the norm of the vector. Okay, so a vector multiplied by unitary matrix as the same norm of the vector, so we can drop the u. So now we have sigma v transpose x norm. But now, right, so Vt is also a unitary matrix, so V transpose X can be another vector, let's call it Y. So now we have that this is the max of sigma Y square, and this is the diagonal matrix, right? So the best way to maximize the norm, right, is to put all of the weight of the vector Y on the largest component of the diagonal, right? And this corresponds to the maximum eigenvalue. Okay, and so this corresponds to the maximum singular value. So here we use the fact that the induced norm of u is equal to 1 and the induced norm of v is equal to 1, and the sigma is diagonal. Okay, very nice, very nice. So the Euclidean norm of the matrix is equal to the largest eigenvalue. Very nice. Now, what about the norm of the inverse matrix? Of course, we assume that A is full rank and square, so that A to the minus 1 exists. And you do the same calculation. And now you notice that you're taking the inverse of the SVD of a matrix. And this is very easy, actually, right? Because these are all unitary matrices, so the inverse is equal to the transpose. And the only thing that we have to worry, right, is that is to determine the inverse of a diagonal matrix. But of course, the inverse of a diagonal matrix is just is obtained by inverting each of the elements of the diagonal. And so here we obtain that the inverse of the norm of the inverse in the Euclidean norm is the smallest is the inverse of the smallest singular value. Okay, so very nice. Now we have our pseudo inverse. So this is, we follow the same description as before, but now we know that this sigma mean is not going to be equal to 0 because we prevented the elements from going to 0, we set them to 0. So now this is equal to 1 over sigma r, and the sigma r is the smaller non-singular value. Okay, so since the pseudo inverse has been sort of numerically stabilized, right, artificially made to behave well, then we know that this will hold. And now we define the condition number of a matrix. Okay, so some of you already had it in your presentation. I don't know if you just used ChatGPT to obtain the number and didn't quite know what the number was. But basically, the condition number of matrix A is equal to the norm of A times the norm of the pseudo inverse. Okay. So if the matrix is full rank, then the rank is equal to the minimums between M and N. There are no zero value. So this is equal to the ratio between the largest and smallest singular value. But if the rank is the matrix is rank efficient, then the rank is less than the minimum. Then the sigma square mean is equal to 0, and so it will go to infinity. Very good. Okay. Now we keep building. We go a little bit more. Yeah, we have 5 or 6 more slides, so bear with me, guys. So another trick that we can do with SVD, which actually is the beautiful application of SVD that we all love, is as follows. Okay, so we say that we can represent the matrix as outer products of the left eigenvectors and the right eigenvectors scaled by their singular values. Now we say that we order this one here from the largest to the smallest. So now we have a concept, right, of approximating the matrix with a low rank matrix by doing the following: going to the smallest eigenvalues and eliminating some of the smallest eigenvalues. Okay, if we do this, right, we are sort of throwing away some outer products that have low weight in some sense, right? And we are creating some sort of approximation of the matrix in our mind, right? So the concept is not immediate, right? The first time that you encounter it, then it starts making more and more sense as you handle it in your mind and in your use of it, right? But the idea is clear, right? So you express the matrix as a sum of outer products, and then we say, well, we can order this outer product according to the magnitude of the singular value, and what we can do is just throw away the smallest singular value. So as it turns out, This operation corresponds to the best rank K approximation of an M times N matrix. Okay, so if somebody tells you, "Oh, we want to approximate a matrix with a rank K, and we want the following to be minimized," which is the norm of the error, right? When you take A minus AK. Okay, so if we set up the problem in which we minimize the error of A minus AK over the choice of AK, such that the rank of AK is less or equal than K, then the solution will be take the SVD and just retain the first K largest singular values. That's it. Then the rank will become equal to K because these components are all orthogonal components, right? So you reconstruct the SVD decomposition of the AK matrix by just using this as U, sigma, and V matrix. The error is equal to the linear combination of these objects, and we saw that this is the norm. Sorry, this is also a matrix with a certain singular value, and we know that the norm of this object is equal to the largest singular value. And in this case, the largest singular value is the K plus 1 singular value, which is the first singular value that we put in the error that we throw away. So now, not difficult to imagine that this has a lot of useful application. So let's say that we take this image. I think you should know which campus is this. I think it's, yeah, maybe Princeton. I don't know which campus is it. No, this is University of Illinois. Sorry, this is University of Illinois at Urbana-Champaign. So here there is an image, a black and white image. So this we represent the pixel as number between 0 and 1, as we did. And so what we do is that we represent this matrix as U sigma V transpose. So the matrix is 500 times 1000 or something. So this is the usually a UV representation where we have this block of zeros on this object. And then we have this. And then what we want to do is that we throw away this 50, we just keep the 50 top eigenvalues, 50 dimension, and you see that this effectively created a very good approximation of the matrix, right? So the error is small in the sense that the A2 norm of the matrix is pretty small. Very good. Very good. So let's just see one more application of the SVD, which is in order to solve system of equation, right? So if you have a square matrix, you want to solve AX equal to B, then you do the SVD, then you know that you will be first solve sigma times Y equal to U transpose B. U transpose, it's a simplified inverse, right? Because this is a unitary matrix, so it's easy. This is diagonal, this is easy. And then you do X equal to V times Y. So the cost of solving becomes N squared because there is no inverse and there's just the diagonal matrix, and you have to do back substitution. And then you have to calculate the decomposition. And we saw that the decomposition takes N cubed. So if you have to solve more than N times this system of equation, then you're better off computing the decomposition first and then applying it multiple times. And that's it. And that's it for today, guys. Okay? Good. So next time we continue from this set of slides. I will release the challenge this Friday. If you have any questions, let me know. We say goodbye to the people over YouTube.